In chapter 3, we talked a little bit about polynomials. We did some different types of polynomials, but really the majority of our work was with quadratic equations, especially. And that quadratics are still a polynomial, but now we're going to get into doing some of the same things that we did with quadratics, but now we're going to do it with all different types of polynomials. We're going to find out what are the zeros, just like we did with quadratics. We're going to find out how many zeros we're going to have, what kind of zeros they're going to be, and we're going to have some different methods of being able to get there. But what we're going to start with is identifying a polynomial. So if I were to give you a polynomial that looks like this, the first thing that we always want to do is we want to put that polynomial into standard form. Standard form simply means we're going to start with the highest exponent and we're going to work our way down to the smallest exponent that we have. And a lot of times it'll already be in that format, but if it's not, we want to put it in that form because a lot of things that we do need to be in standard form. And when we look at different things within that polynomial, we want to be able to just look at it and say, this is already in the form of highest to lowest. So if I were to rearrange this polynomial into standard form, 4 is the highest exponent. Whatever is in front of the 4 or the highest exponent is going to stay with it. So we're going to start with negative 3x to the 4th. Then the 7x cubed is going to be second, and then the negative 5x squared would be last. So we go 4, 3, 2 as far as our exponents go. The numbers out in front really don't matter as long as they stay with what we have. And in some cases, we'll have an x and then a constant at the end of this as well. But sometimes we don't have all of the different parts listed in our polynomial. And so for this polynomial, that we just have to rearrange everything that we have, and that would be our rearranged polynomial in order of standard form. When we name a polynomial, we name it based off of its degree. And the degree is simply the highest exponent of that, okay? So I'm going to look at a couple of different names. All of these names, or most of them at least, should be familiar to you. We're going to go up to 5. We really don't go any higher than 5. If we do go higher than 5, then we just call it like a 6th degree or a 7th degree, but we don't see those very often. Okay, so a degree of 0. A degree of 0 would be like a number, like 8. It doesn't have any variables with it. It doesn't have anything attached to it. It's just a number. And we call that a constant. Because if I have 8, 8 is always 8. It can't change. And so it's going to stay the same. Something remains the same throughout, then we call that constant. 1, a degree of 1, we've seen this. This kind of goes back a lot to like the very first chapter. We saw a lot of linear equations. Slope-intercept form, for instance, y equals 2x plus 3. If I graph it, it makes a line. It has an exponent of 1 on the x, so we call that a linear polynomial or a linear equation. The degree of 2, we saw a lot last chapter, are quadratic equations. It makes our U-shaped graph, and sometimes it could open up, sometimes it could open down. But we dealt a lot with quadratics, finding the vertex, and all of those different things with that. These last 3 we haven't seen a ton. We've maybe seen them a little bit. Cubic, we've seen a little bit of the cubic graphs. That's where it makes like the snake-like graph. Has a degree of 3. And then the last two, we really haven't seen these very often. Quartic is a degree of 4, and a degree of 5 is quintic. And it goes kind of off the prefixes, like for instance, quint means 5, like quintuplets would be 5 babies, which, oh my gosh, right? That would be pretty miserable if that was happening, I would think. So, but quint is a prefix. And like I said, if you get any higher than that, then we go 6th degree, 7th degree. And we could call this a 5th degree, but more specifically, we call it quintic. You might remember back like when we talked about polynomials in Algebra 1 and Algebra 2, we talked about trinomials and binomials and monomials and things like that. We don't really name them using the number of terms because especially when we get into these higher ones, we're looking at like having 4 or 5 terms sometimes. And so when we get to be that long, then we don't really have any special names for it. We just call it a polynomial. So really when we name these, we just call them polynomials and we don't necessarily have to worry about trinomial, binomial, and things like that. Though, I mean, they still exist obviously, but we just don't usually use those to name it. One of the things that we're going to do today is name some of the different things, and some of the things that we're going to name here are going to help us with some of the things that we do. Okay, so the first one is, what is the leading term? This is why we put it, one of the reasons why we put it in standard form, because if I look at the original one, a lot of people will just look at what's in the beginning and call that the leading term. But as I rearrange it and put it into standard form, the leading term is actually, once it's in standard form, it's the term that's at the front of the polynomial. So it has to have the highest degree on it. So the entire term is negative 3x to the 4th. The leading coefficient, we've seen that term before. Leading coefficient, a coefficient is the number in front of a term. So that would just be negative 3. X to the 4th would be the variable. Negative 3 is the coefficient in front of that variable. We're going to talk a lot about degree today. And as we go throughout the rest of this chapter, degree is a really, really important part of polynomials. The degree of this one is, once again, the highest exponent in the polynomial. And once we've put it in standard form, then it's always going to be the one at the beginning. Okay, but sometimes what throws people off is they'll look at this and say, oh, it's 2 because it's out in front, but that's why we want to rearrange it. And once it's in standard form, it's the highest exponent, which in this case would be a degree of 4. Okay, and then when we name it, we're only going to name it by its degree. And because this one has a degree of 4, then we call it a quartic. So those are just some different things that we use to kind of identify the parts of that. But probably the most important thing is the degree. The degree is going to tell us a lot of different things about that polynomial. Okay, the next thing that we're going to do is talk about what we call the leading term test. I kind of abbreviate it as LTT. The book doesn't really do that, but if we ever had to do the leading term test, which we will occasionally, then instead of writing out leading term test, if you want to abbreviate it and go LTT, I'm fine with that. So I'm going to give you a polynomial. And all that the leading term test does is it tells me what direction this graph is going to open at the beginning and at the end of the graph. And so like for instance, if I had a quadratic, it's either going to be up, up, or it's going to be down, down, right? Because it's a parabola. And we know those are my two options. And there's really 4 different options that we're going to see here. And we're going to kind of talk through about how we decide which one's which. Okay, so the two things that we're going to use are the degree, and the degree can either be even or odd of the polynomial. And then the lead coefficient would either be positive or negative. Those are the two things that we have to decide, okay? And I'm going to try to give you some real basic examples here of how we can kind of think about what this graph should look like. And here's what I'll tell you. Can we put this into our calculator? Sure. But there will be graphs as we go throughout this chapter that they don't look very good. We're going to have to like zoom in, zoom out. We're going to have to kind of change the window to get a real good picture of the graph. But by doing the leading term test, I know what the ends of this graph are going to look like without ever having to graph it. Okay, so could you graph it? Absolutely. And as I've told you since day one this semester, the calculator is going to be a really good tool, but sometimes it doesn't display very well. And sometimes they give us some kind of funky looking graphs, but we kind of know what this is going to look like just by the basic idea of the graph. So, even versus odd. Even would be 2, 4, 6, 8, obviously, an even number for my degree. So let's think about a really easy one that we've done before, like quadratics we just got done with, right? Quadratics have an even exponent because they're x squared. So if I graph a parabola, it's either going to open up in both directions or it's going to flip upside down and go down, down. So if I have a positive coefficient, like 2x squared, right, then it's going to be a parabola, and the graph is going to go up, up. It's going to start up, and it's going to end up. And that would be the same for a quartic graph. We're going to see some quartic graphs. Instead of a U shape, it kind of makes like a W shape where it kind of comes down, it has another hump in it, and it kind of ends going back up. Okay, and they're all going to look a little bit different, but it still ends up, up. It's going to start up, and it's going to finish up. If I put a negative in front of that, so like negative 2x squared, it's going to take that parabola and it's going to flip it upside down, right? And so instead of up, up, it's going to start down and it's going to finish down, okay? And once again, anything that has an even degree, 2, 4, 6, okay? And probably 2 and 4 are the two most common ones that we're going to see. It's going to either go up, up, or down, down. Okay, if it's an odd degree, and in this one I kind of think of, we could think of a cubic, but I even think of like a linear, like a positive, if I have a positive leading coefficient, a positive slope, that means it's going to start down and it's going to end up, right? It's just a line. And so it's going to start down here and it's going to finish up here. And so it starts down and it's going to finish up. So they're going to finish, or they're going to go in different directions. It's going to start in one direction, it's going to finish in the other direction. If I think of like a negative slope when I do a linear equation, it's going to start up here and it's going to finish down here. And so it's going to start up and it's going to finish down. And those are your 4 different possibilities. If I did a cubic polynomial, still odd, and it's still going to do the same thing. It's going to either start up and end down, or it's going to start down and end up, but they're going to be going in different directions when we do it. And so that just kind of gives us a basic idea of what the graph's going to kind of look like before we ever even graph it or do anything with it. So as I look at this example here, the only thing that I care about is the leading coefficient, okay? The leading coefficient is what we're paying attention to, and the leading degree, okay? Just make sure that it's already in the standard form that we want it in. So here we have a degree of 3. So my degree is odd. And my leading coefficient is negative. So if it's odd and negative, we go odd, negative, then it's going to be this guy right here. It's going to start up and it's going to end by going down. But those are our 4 choices, one of those 4. And I kind of gave you some other options or ideas as we went through it with like quadratics and things. So I'm not going to do a ton of examples there. We don't use the leading term test a ton other than just kind of using it as we think about what the graph is going to look like and some of those kind of things. We did this a little bit in the last chapter. If I gave you a polynomial of some kind, I'm going to give you a couple of possibilities, and it's going to ask us the question, are these zeros of a polynomial? Okay, well, there's a lot of different names that we use for zeros. Zeros are the solutions. Zeros are also the x-intercepts, okay? And so when I ask you if it's a zero, I'm going to give you some possibilities here. F of 4, F of 5, and F of negative 2. Okay, and there's a couple of different ways that we can verify if these are really zeros, okay? If it's really a zero, when I plug 4 into this equation, it would give me a solution of 0. It would equal 0, okay? So that's one of the reasons why we call it a 0. If it gives me any other value other than 0, then it's not a 0, okay? All I care about is does it give me 0 or not? Well, when I give you like multiple things to check here, instead of taking 4, plugging it in, seeing if it equals that, and then taking 5 and plugging it in, and then taking negative 2, that takes some time, right? And so rather than doing that, what we could do is we could put this function into our calculator, okay? Use our calculator to help us out a little bit, and then check each one of these individually to see if they're zeros. All we really have to do is look at our table, okay? And we're going to look at those 3 values that we're checking, 4, 5, and negative 2, and see if the value that I get back is 0, okay? That would be a really quick and easy way, rather than plugging all 3 in separately. Both of them would work, but we're trying to do the easiest, quickest way possible, right? So let's put this into our calculator. Four gives me a value of 0, so we would say yes. 5 gives me a value of, and so both of those would be no. I don't really care what the value is. If it's not 0, then it's not a 0, okay? And that's all we have to do when we try to determine if it's a 0. We're going to spend a lot of time throughout this chapter talking about the zeros of the polynomial. And so once again, remember the zeros are, we did it with quadratics last chapter, where does it cross the x-axis, okay? And so we're going to continue using that. If we have a cubic polynomial, and we'll talk more about this as well, when it was a quadratic, we said it could cross up to 2 times. When it's a cubic polynomial, it could cross up to 3 times. So it could have been where all 3 of these were a yes, because it could cross the x-axis 3 different places because it's a cubic polynomial. But all we want to do is determine if yes or no, it's a polynomial. Okay, the next thing we're going to look at is finding zeros different ways, and then talking about what the multiplicity of those zeros would be. And multiplicity is a little bit different, but it just tells me how many times could that 0 possibly occur. And one of the things that we talked about, like when we looked at parabolas last chapter, was sometimes that parabola could come down and hit the x-axis at a number, and it could bounce back up. So it doesn't necessarily have to happen or cross the x-axis twice. We call that a multiple 0. When it comes down and hits the x-axis and goes right back up, or if it comes up and hits and comes right back down, we call that a double root, okay? And so that counts as really 2 zeros, because it comes in and leaves from the same value. It doesn't actually cross the x-axis at that point. And so if I gave you a possibility, and there's a couple different forms that we're going to look at. We saw this a little bit with quadratics as well. Just kind of draw that similarity of what we've seen. Factored form is where it's already been factored. In a lot of cases, factored form is really easy to find the zeros, okay? So the first thing, if I wanted to find the zeros of this, I'm going to take both of my factors, and I don't necessarily have to put it in parentheses. I probably should have left the parentheses off. But we're going to say x plus 3 equal to 0, and we're going to say x minus 1 equal to 0. Pretty easy equation to solve. X equals negative 3. X equals 1. Okay, and when I look at this, and here's what I'm going to tell you. This one has a degree of 2. This one has a degree of 1. If we were to multiply all this together, it would actually have a degree of 3 total. So we basically have to account for a degree of 3 in some shape or form. And so what we say here is because this one has an exponent of 2 on it, then we say that it is a multiplicity of 2. It happens twice. That's why we call it a multiplicity. If there is no exponent on it, then it's assumed 1. So we say that one has a multiplicity of 1. Okay, and here's what that means. If I were to graph this, and if you wanted to, you could put this into your calculator and graph it, and maybe we'll even do it for this one just to kind of show you what's going on here. These are the two places that this graph should cross or touch the x-axis. And so if I put this in real quick, is it has a multiplicity of 2, and what happens when I have a multiplicity of 2, if your multiplicity is even, then that means your graph is gonna, I call it bounce. It's not really a mathematical term, but that's kind of the way I envision it. It's gonna come up, it's gonna hit at negative 3, and it's gonna bounce right off that x-axis. Okay, it's not gonna go through the x-axis. If your multiplicity is odd, then it will go through the x-axis at that point. And that's what happens at 1. I showed you the graph. It came up and it went through at that particular point. So just if I drew a sketch of this, it's going to bounce, it's going to turn, and it's going to come back up through at 1. And that's kind of a real quick sketch of that graph. But this helps me to kind of graph and give me a basic idea of what that graph's going to look like. Obviously, we can use our calculator for that too. But understanding what the multiplicity of 2 is going to tell me is really important. And it tells me how we can kind of come up with our zeros for that. Okay, this one I'm not going to graph it, because this one is a big, nasty polynomial. I would not want to put one like this into standard form, because I have 1, 2, 3, 4 different factors. If I wanted to put this into standard form, I'd have to multiply all these together, and that would be a pretty lengthy process. Okay, we're not going to do that. That's where factored form really comes into play. But because I have 4 separate factors, you have to have an x on it to be considered a factor. We're going to set all of those factors equal to 0. The first one, the x here, does not have a plus or minus attached to it. You don't have to worry about the x squared here either. Don't worry about the exponent until the very end. So if it doesn't have a plus or minus on it, we just set it equal to 0. X plus 3 equals 0, x minus 1 equals 0, x plus 4 equals 0. X equals 0 has a multiplicity of 2 because my exponent is 2. X plus 3 squared is going to be x equals negative 3 with a multiplicity of 2 because my exponent is 2. X minus 1, we set it equal to 0. We get x equals 1. There is no exponent on it, so that's assumed to be a 1. And then finally, x equals negative 4. And that has a multiplicity of 4. So these three here would all bounce at the x-axis at that point, and this one's odd, so it's going to go through the x-axis at 1. I'm not going to graph this one, but just so we kind of understand what's going to happen with the graph at that particular point. So factored form is pretty easy to come up with the zeros and identify what those zeros are going to be, set it equal to 0, solve for x. Okay, this next one, what if we're given a function that's in standard form? This is a little bit more work involved. And your calculator can definitely be a tool, especially later on in the chapter when we talk more about these. But we also kind of want to know how to do some of these algebraically. How can I get some of these zeros algebraically? And then I can kind of use my calculator to verify what's going on. Well, when it's in standard form like it is here, not factored form, it's already in highest to lowest form like we want. Make sure that's the first thing. And most of the time it will be, but if not, we want to put it in that form. And this one's going to be a little bit different, okay? We have to find the zeros and the multiplicity of these zeros, okay? And we haven't really done one with x to the 4th before. And so it's a little bit different, but we're going to use a process that we're pretty familiar with. What we're going to do here is we're going to factor this. We want to get it into factored form. So somehow we want to be able to factor this polynomial. Well, we've done it with x squared, but this has x to the 4th. And we can use a lot of the same methods on x to the 4th as we did on x to the 2nd. So in this case here, if this was x squared, and we have 3 terms here, I could do product and sum, right? And I could do the same thing here. I could say, what has a product of 3 and a sum of -4? What two numbers make that work? -3, -1, okay? Now here's the thing that's a little bit different. The first term in each parenthesis will be x squared, because this has to be x to the 4th, right? So x squared times x squared gives me x to the 4th. So make sure it's not just x times x like we're used to. And then the two numbers that we just came up with would be x squared minus 3 and x squared minus 1, and those can be in any particular order. And this is where we're going to use some of the methods that we talked about last chapter to kind of bring it in here. If I wanted to factor and then solve these two, the best way to solve these two would be to use the square root method. There is no b value, right? There's no x in the middle. So I could now take x squared minus 3 and set it equal to 0. I could take x squared minus 1 and set it equal to 0. And then I could solve both of those for x. And remember when we did the square root method in the last chapter, we always want to make sure we put plus or minus on our answer. Same thing over here. X squared equals 1. I take the square root of both sides, and I get x equals plus or minus 1. Okay, so a couple of things that I'm going to talk about here, and then I'm going to show you the graph. We're going to graph this just to show you how everything kind of fits together, okay? We had x to the 4th. And what that means is this graph could cross the x-axis 4 times. And we have 4 different zeros. We have 2 here, plus or minus radical 3, and plus or minus 1. So it has 4 different zeros. And so what we would say here is that these all have a multiplicity of 1. They all happen one time. They're all going to cross the x-axis at those 4 particular points because we have a degree of 4. This is why doing this algebraically is kind of important, because radical 3 is not a nice whole number. 1 would be pretty easy to identify, right? But if I'm looking at my graph, I'm not going to be able to look at it and say, oh, that's radical 3. That is an exact answer. It would give us a decimal answer. And so just to show you this real quick here, this is one we have not spent much time with this semester, but I think you've seen it before. It's another one where we're given a polynomial in standard form. So we're trying to find the zeros of this polynomial. And so we know that we're probably going to have to solve it algebraically somehow. And there's going to be some other methods that we're going to kind of incorporate to help us out as we go throughout. But for right now, factoring is going to be one of those methods, at least for today. And so I can't do product and sum here because I have 4 terms. And it's a cubic polynomial, right? And so the factoring method that we're going to do here is what we call grouping. And I think we had one problem like that. It was kind of a weird problem that was when we solved quadratics, there was this one problem in there that was grouping, and I told you eventually we were going to talk about grouping, so I think we did it together. We're going to group this into 2 groups of 2. And we're going to take a GCF out. So out of the first 2, I can take out an x squared. And if I take x squared out of both of those terms, that leaves me x minus 2. Out of the second 2, and this is where you got to be a little bit careful, 9 and 18, I can take a 9 out, but I want this to end up exactly like this. And so what I'm going to end up doing is I'm going to end up taking a negative 9 out. And if I take negative 9 out, I'm dividing both of these terms by negative 9. So negative 9x divided by negative 9 would just leave me an x. And then 18 divided by negative 9 would give me a minus 2. Okay? We want these 2 parentheses to be the same. If they're not the same, we're going to have to go about it a different way. They're the same. And then what we're going to do is we're going to combine the outside pieces together, because that's my GCF, and we're going to leave that common factor alone. But we only write it one time. I know it's listed here twice, and what a lot of people want to do is they want to list it twice, but this is a common factor of those 2, so we only list it one time. And if I look at x squared minus 9, what can we do with x squared minus 9? How could we factor that? What factoring method? What'd you say? Take the square root of it. Yep, this is good old dots right here, right? Difference of perfect squares. And so I could break this up. And that would be x plus 3, x minus 3, and we still have x minus 2. All right, so what we have here is these are what we call the factors of the polynomial. If I were to multiply these 3 things together, it would get me back to what I started with. Okay, so we got the standard form and we got factored form. We've seen both. Sometimes this is what's given to us, sometimes the standard form is given to us. The zeros in this case would be x equals negative 3, positive 3, and 2. I'm not going to write out the equation for each one of those because it's just a one-step equation, right? We're just going to set it equal to 0 and solve it. So I think we've done that a couple times already. I think you kind of start to see the pattern. We could just set it equal to 0 and solve. Those are the 3 zeros, and they all have a multiplicity of 1. They would all happen one time, okay? If we were to graph this, I'm just going to save a little bit of time here. I'm just going to graph a real quick sketch of what this is going to look like. If you wanted to put it in the calculator and kind of verify. I'm not real worried right now about where those humps are at. I just am drawing a real quick sketch and just kind of showing you it's a cubic graph, okay? It's crossing the x-axis in 3 places. It's crossing it at -3, +2, and +3. The 3 places that we just identified are the 3 places it's going to cross the x-axis, and they all cross it one time. It doesn't bounce or do anything else. It goes ahead and crosses the x-axis at those places. So trying to just show how everything ties together, right? That's a really, really big part of this, and we're going to continue to see this a lot throughout the chapter, using some of these ideas and rules that we're going to be looking at here. Okay, I will tell you this as well. Another thing that they talk about real briefly in this lesson, we've already done this. They're going to ask you for the relative min and max, and this would be something that you would want to actually use your calculator to find, okay? Because this right here, this point is where it reaches its relative max. This point is where it reaches its relative min. And those probably, in some cases, are going to be big old long decimals, okay? And so they're going to ask just around to nearest tenth, hundredth, whatever. But relative min and max are 2 things that you could find on your calculator. We've done that before, so I don't think there's much there to talk about. But if you see it in your assignment today. And then the other thing, the one common topic we keep coming back to, domain and range, but really in this case, domain, what would the domain of this graph be? It's just going to be all reals, right? This graph's going to continue to stretch left to right in both directions forever, okay? So they don't ask us about domain a lot because most of these graphs are going to have a domain of all reals. So it'd be answering the same question over and over again, essentially. But the range, not all of these will have the same range, but in this case, what would my range be if I go from low to high on my y-axis? All reals still, right? And sometimes it'll be all reals. If it's a parabola, we saw that a little bit in the last chapter, where if it has a minimum point, it's going to go from the minimum point up, or it's going to go from negative infinity up to if it has a maximum. So if it doesn't go continuously forever, top to bottom, then it could have a little bit different range. So that's just a different thing that we didn't talk about. Okay. There's one other thing, but I think I'll probably start tomorrow's lesson with that one because it's another one I want to talk about, but just for the sake of time.